Deep learning is a subset of machine learning where neural networks learn from training data, and as a result, they are able to make decisions after the training. The data used in deep learning are traditionally text structured, such as in database or CSV format. In many real-life applications, however, a complex graph structure is required to model the data set. For example, in social network graphs, protein molecules, or bicycle road paths. This leads to the development of graph neural networks, which are neural networks specifically used to process graph datasets. This project uses graph neural networks. Neural networks are black box in nature. In this project, we want to understand why the model chooses the decision that it makes. In this project, we use DGCNN and GCN architectures. Let's take a look at each of them. This is the architecture of DGCNN. Here, a novel sort pooling layer is used to sort vertices by color before the final multi-layer perceptron layer. This is the GCN architecture that we use. It uses a GAP layer before the softmax layer. The explainability methods that we used are deep lift and contrastive gradient. Deep lift uses a baseline to assign contribution scores and take into account both positive and negative contributions. This may give better insights in terms of explainability. Contrastive gradient measures the gradient of the output with respect to the input. The absolute values are then taken as feature importance. To compare between the metrics and architectures, we define three quantitative metrics: fidelity, contrastivity, and sparsity. Fidelity refers to the difference in accuracies of the model before and after occluding salient nodes. Salient nodes are important nodes to the class which are identified by the explainability methods. The notion of contrastivity is that the salient features between two classes should be as different as possible. This is quantified by measuring Hamming distance between the binarized heat maps of two classes. The idea of sparsity is that the number of salient nodes for each class should be as small as possible. This is especially important when dealing with large graphs. Following is the result of the experiments on MuTech dataset. Here, Deep Lift and DGCNN shows the highest result on both fidelity and contrastivity scores, while CG plus GCN gives the highest sparsity score. Using TOX21 dataset, Deep Lift does better again in CG in terms of both fidelity and contrastivity. Deep Lift and DGCNN gives the highest contrastivity score, while Deep Lift and GCN gives the highest fidelity score. Meanwhile, CG does better again in sparsity, where CG plus GCN gives the highest sparsity score.